So welcome to the first actual lecture of statistical learning in practice. The first thing I want to do is just to give you a very, very brief idea of the parts that will make up the course. So we're going to have, I remind you that I'm uploading everything that I will write here. So the course is really, fundamentally what is called, I presume many people here are interested in machine learning. So it concerns supervised learning. So we won't see anything else than supervised learning. And supervised learning, essentially, you could think of it as being regression, but so that will be the first, so the course contents, let's say, so course. So I presume you can see that, yes, because I can see people writing down. So, so course contents. Maybe just, okay. Let me go now to the lecture room. Okay, so yeah, the course contents. First of all, I said regression models. Okay. This is regression, and I will probably shorten regression as reg. Regression models. Then actually probably an even more common example of supervised learning is classification methods. We'll see that classification is actually a special case of regression, but because of its importance, then we'll just put it separately. Classification models. And then third, we have also some sort of supervised learning class of models, which is essentially, the difference with these guys is that we're going to lose the independence. And these are time series. Yeah. Time series models. Yeah. Okay. So these three parts of a course will have approximately 11 out of 24 sessions, and then 9 out of 24, and then 4 out of 24, just so that you get an idea about the contents. Okay, so let's start with regression models. So regression models. What is the, what's the setting with regression models in general? So we have data. Remember, in statistics, we always have to think of, what data do we have? And what is the objective that we have in mind? In fact, I would say, so I advise a few organizations and on data analysis, and in fact, I would right now go against what I just said, because that's what people tend to do. And what turns out is that, there is something called essentially the design of the experiment that comes before collecting the data. That is key, and that many companies tend to sort of not think too much about. And I would say this is previous to data, previous to data and objectives, because you should have an objective in mind before you actually try to collect the data, because you should collect the data according to the objective that you have. Yeah, but because this is a mathematics, it belongs to part 3, then we can assume that we are given some data. We don't need to think about the experiment, how to design it. So this is how I'm going to basically phrase things. Yeah, but in practice, you should always take into account data and objective when you're trying to, when you're designing what data you want. Okay, so we have data x1, y1. So we have pairs actually of data, and I write these as lower cases because these are the actual, sort of numbers that we get. Yeah, and these guys are going to belong to a product space. So this is calligraphic X times calligraphic Y. Calligraphic X is generally referred to as the sample space. Sample space. and usually we have, let's see, so usually okay, so usually what we have is that X is, in RP with P greater or equal to 1, and Y is in the real numbers. And these guys have a name, right? So they come in pairs. So the first bit, which may be multidimensional, is what is called the covariates. Covariates. Sorry, I'm going to try to stick to writing in capital letters just because my writing is terrible. So it's just a way of somehow avoiding confusion. And they're also called predictors. So just for this, I will make an exception. And then regressors, or independent or explanatory variables. Okay, and then these other guys are, the targets or the responses. They will be labels in classification. They have all kinds of names, and then also dependent variables. Yeah. Okay, so why do we call these guys dependent variables and the other guys independent variables? Well, that's very simply because the objective in a regression problem is precisely to find a good good functional relationship relating y, or maybe the y's to the x's. Yeah. And I'm being not very careful here with the way to express it, but I like just communicating things in a bit of a simple way. Okay, so what is this? What is underlying this? This good functional relationship between the two is really what a regression model is. Yeah, so a regression model. Okay, I do want to make a warning here. Because it will, it sort of underlies the philosophy that I have. And, it's not that I have it, it's just that it is a good philosophy to follow, at least if you come from statistics. And I will explain this in a second. So let me just write it as I'm talking. So models, you should always keep in mind that models are only an attempt to approximate reality or to describe reality. Yeah? Okay, so any conclusions? Arising from them? It's very important that we have, at least for now, human supervision in some sense. So these must be interpreted with care. Yeah. So I will comment on all of this in a sec. And let me also say that interpretability is fundamental So I will try to be more sketchy than this generally, so that we don't have this sort of slow pace. So it's fundamental in sensitive applications. So you should be thinking of, medical applications, especially, but also, self-driving cars, for instance, where human safety is in play. And something important to also keep in mind is that traditionally, this is achieved by simplicity. Of, in this case, the underlying model. Yeah? Okay, so what do I mean by this? So what I want to say is, always keep in mind that a model is just a model. Yeah, reality, we don't know what reality is, and a model may well describe some things of the observable reality, but it may also not be perfect, and it may also change in time. The parameters of your model may change in time, and maybe you shouldn't be trusting your model all the time. And so really, the human supervision, at least for now, we haven't learned, well, I guess we have a bit, but, so far, humans have to be sort of analyzing with care any conclusions, yeah, that come out of a model. And the other thing is that for instance, for medical application, it's very important to be able to explain to a doctor how the algorithm made this or that conclusion. Yeah, otherwise the doctors will not trust it. Because of course there's a human life in play, and so it is really important that they can be interpreted. And a way to get interpretation or interpretability is precisely through having simplicity. So what I want to say with this is, it's not really a criticism to machine learning and deep neural networks and all these things, which are amazing at anticipating or just so they're really good at solving some problems, essentially, but they're a bit like black boxes. So for they're not good for all applications, at least yet, until we can explain them better. And so this is in some sense a defense for simple models, which are also very important for this reason. Yeah. Okay, so let's move on, and let's actually start with generalized linear models. So this is all. So these things, I'm going to go a bit fast, or try, because I talk too much, but generalized linear models are a class of models that you should be sort of familiar with, at least the linear model. So the linear model is a prerequisite of this course. And if you're not familiar with it, then I invite you, and really strongly invite you, to go to my lecture notes from the Part 2 course, Statistical Modeling. So these you can find on the website of the course, and take a good look at that. So we'll have a brief sort of recap of it here and in the first practical session, but still you should be familiar with any results on linear models, yeah? That at least those that are in statistical modeling. Okay, not theoretical. You don't need to know the proofs exactly, but yeah, certainly be comfortable with it. Okay, so let me give you an example of a generalized linear model. So that's exactly the linear model. So linear model. Okay, so what is the linear model? Well, let's start with some data. So imagine that we have some data that looks something like this. So we have, some. Sorry, that's not very. Yep. Okay, so let's imagine that we have some data that looks like this. So these are the covariates, and this is one-dimensional covariates. and this is the targets or the other names that we were giving it. And, you know, if you see this cloud of points, then you could be thinking, well, you know, I mean, this is maybe it's not badly described through a line, something like that. And then once you have that, then you start thinking, well, then yeah, it wouldn't be too strange if I postulated that you know, the distance here, so these errors that we have here, actually they go up and down around this line value, and so why not for them to, you know, to have some expectation to be 0, and maybe, you know, they seem to have a similar dispersion. This guy is farther, but that's not too bad. So maybe they have constant variance, and so that we simplify the analysis, then we could also assume that they are independent. Yeah. So that's basically what the linear model postulates. So this is, by the way, p equal 1, as I was saying in words. So then the linear model, it postulates, you know, remember, this is just a model. It's, you know, some attempt to approximate the points that we see here. And so it postulates that each observation, and note that now I've written it in capital letters, the y. I'll explain why. So capital letter, why is that? Well, because we consider this guy to be random, the left-hand side. And so if we have a realization of it, then it would be a lowercase as the ones that I was giving you. Then the x's are lowercase. I'm keeping it lowercase here, which is, you know, what is called fixed design. But anyway, you know, I'm just forgetting about any possible randomness, just for simplicity of the x's. Okay, and this is, you know, postulates this form for some beta in RP, that this is unknown, and this is actually, you know, if we're thinking of statistics, this is the parameter that we wish to estimate, at least the first one. And then the epsilon i's are going to be such that, so this is what I was mentioning, such that each of them is centered, and then they all have the same variance, and we're going to assume that the covariance between two of them is 0 whenever they are different. And so remember, these two guys, of course, go from 1 to n. Yeah, so we have n, small n is what is called the sample size. And I will always, or at least always try to, so I didn't say it earlier, but yeah, this is the sample size, but I will always try to write it as lowercase n. And note that if you're reading machine learning references, or, you know, the literature in general, then they tend to denote the sample size by capital N. So that's just a difference in the conventions that we have in the two fields. Okay, so in matrix form, let's write this model in matrix form. So I'm sorry for those who know the linear model inside out, but it's good so that we can motivate the rest of the whole regression models section. Okay, so in matrix form, what we have is that y equals capital X beta plus epsilon, where y is the vector of y's. X is what is called the design matrix, and this is the vectors of covariates transposed. So this is the design matrix. Precisely this terminology, so the name design matrix comes from design of experiments, the field of design of experiments, which is what I was sort of talking about at the very beginning of the lecture. You know, you need to design how you need to design your experiment first before you collect the data. So it comes from that field, which is a fascinating as well field. Okay, and these are the errors. Yeah. They may be measurement errors. You know, maybe you're taking some measurements here, So I'm looking at the graph, by the way, and these are the errors. Or it could be just simply that this data is not really from taking measurements with a machine, but rather taking some measurements of people doing certain things, and your lack of knowledge or all of the causes that are giving rise to these observations that are around this line. Well, you try to describe that lack of knowledge through some errors. Yeah. Okay. So generally, what we have is what is called the normal linear model. Okay. So generally, what we postulate is that these guys, they not only satisfy all of these properties, but they are normally distributed. Okay. So they have a multidimensional distribution with, and this is of course the identity matrix with n times n, so that we get uncorrelated entries in the epsilon. And in fact, in the normal distribution, because it's jointly normal, then we get independence. Yeah? Okay, so this is for some sigma squared positive that may be known or unknown. So you can have a model with either option. And again, this is the normal linear model, which we will shorten as NLM. Okay. And in this model, therefore, what we have, because remember, we're interested in understanding y in terms of x, then what we have here is really, this is exactly what we're postulating. We're postulating that the y will be distributed according to normal distribution with this linear mean in the beta with some variance sigma squared in each of them, and actually with independence between the y's. Yeah. Okay, so if you have any questions, remember you just ask in the chat. So yeah, I can see it's not active, so that's good. Okay, so let me now say, the three things that we are assuming in this model. So first of all, what we're assuming is that y is normally distributed, right? So we're making an assumption on the distribution of y. Okay, the second thing we are assuming is that the expectation of the y given the x, and then, you would here criticize me because I said that the x's are non-random, so you don't need to do this conditioning, but in general, one can have the x's to be random. So then one looks at this quantity. And what we are postulating is that, again, there is a linear relationship. So this is linear in beta. Yeah? And then the third thing is, well, we're allowing for a free variance or dispersion parameter. Okay. In this case, it's the sigma squared. Yeah? Okay, so these are the three characteristics of this model, and again, see the statistical modeling notes for inference on this model. So far today, we're going to be talking about models rather than making or statistical inference on them, estimation, confidence intervals, and so on. Okay. So this is good, but these three things, especially the first two, I mean, the third is actually not, it's good, right, that we have some freedom there. So the first two, we're sort of actually restricting things, right, by choosing the distribution and choosing the relationship, or the nature of a relationship. So despite this being actually the most important model in statistics, so despite NLM's importance, it's not always good. Yeah. And remember, I said above, good And I'm a bit I don't want to define what I mean by good, but you will see that it's certainly not good, yeah, for any standards of goodness. So okay, so let me give you two quick examples. So let's look at, for instance, the number of insurance claims, right? So imagine that we're an insurance company, and then we just wish to look at the number of insurance claims that we get according to, depending on, for instance, severity of the weather in whatever way you want to measure this. Yeah, so I'm being a bit vague in this. Severity of the weather. Okay, and this is just normal weather. Yeah, it's not extreme to the other side, but just normal. Yeah? Normal weather. So, you could imagine that if you have normal weather, then you'll get, a certain number of claims. And, as the weather gets more extreme, then maybe, we start having a bit more claims, a few more claims. And suddenly, if it gets really, really bad, then we may get just a lot of claims. Yeah. So then the question here is, if we try to do as before, so if we try to have sorry, I'm messing up the colors, but it's fine. So imagine that we wish to do something as before, so, to have some sort of line here, and then say, well, the errors that we're making with respect to that line, we're going to assume that they are normally distributed. Then that would be quite silly here, wouldn't it? Because normal distribution will not always fall on natural numbers, for instance, and the number of insurance claims is they must be natural numbers, and it may be in fact that this normal distribution goes to the negative numbers, so that's again something non-desirable here. And there is also a lot more structure than just having fluctuations around a line, right? Because clearly here there is some sort of exponential structure behind it. Yeah. So the line doesn't look as the best way of modeling this expectation that we have in there. Yeah. Okay. So let me give you another example. So another example would be the following. So just imagine that we have. So we're looking at the number of hours, okay, so just to keep the colors consistently. So the number of average hours per week studying statistical learning in practice. Yep. And we're going to try to understand the proportion of people passing the course. Yeah. Okay. So if this is 0 and this is 1. Yeah. So, just imagine that I'm doing a social experiment in which I'm going to look at the number of hours that you spend on average studying this per week. And then I guarantee that if you used all of the hours of the week, all of the possible hours of the week studying this course, then I guarantee you will pass, all of you. So if I took, the data for this, then we would say, well, out of those people that did all of the hours of a week, or spent all of the hours of the week in this course, then all of them passed. So, it's M over M for the M number of students who did this. Then also, if we have M students who did 0 hours on this course, then I also guarantee that they will not pass, none of them. So we will have 0 out of M. So this is the proportion here. And then, as you start studying, then if you do a bit more, then a certain number of those that did a bit more will pass, and so on. But actually, as you start studying more, then it gets a lot better. And then how it is, you plateau a bit, and it's actually harder to sort of scrape a few more decimals out of an exam. So then it will look something like this, say. And again, if we try to describe this through a line, then maybe you'll see, well, actually, this is a bit better than before because it's going up and down. But again, if we had a normal distribution, then we would easily go down or up here. And so that wouldn't make sense as a model for a proportion. Again, it may be that they are up and down, but they're so in a very orderly fashion, right? So really what we have here on the line is a different model, yeah? So again, a nonlinear model in some sort of parameter beta, yeah? Okay, so we'll see that these two can be modeled through a Poisson model and the binomial or the logistic regression model. So I will just ask you to keep them in mind for when we introduce these models. So let me now then talk about GLMs more generally. So in GLMs, because these are the models that we're going to be looking at first. So GLM, of course, is generalized linear model. So let me just shorten this. So GLM, okay. So generalized linear models. So the two I mentioned are generalized linear models. The distribution for y is from a so-called exponential dispersion family. Okay, so I don't expect everyone to have seen this. But for a second, what you should be keeping in mind is that this is a this is a family of distributions that includes the normal distribution. Of course, it includes others that will describe these two graphs better than the normal model, the normal distribution, and but that is still simple enough, yeah? Or whose elements are still simple enough. Yeah. Yeah. Okay. So we assume this, and we're going to model this expectation with respect to the x beta, so the same quantity as before. This is what is called a regressor. And this word is certainly abused in this field, because I already said that the x's are the regressors, plural, but this is called a regressor as well. So we're going to do this via a not necessarily linear function. Yeah. And then last, so depending on the distribution for y, we may have a free parameter for the dispersion. Okay, well, actually, maybe I should have said we may have a free dispersion parameter. Sorry, because I haven't defined dispersion, but at least I can say a dispersion parameter. Okay, so this is just like in the normal linear model, but it may be that, given the distribution that we choose, we don't actually have this free parameter. Yeah. Okay. So, and I guess just so we will use the whole hour today, by the way. And actually, I may use the whole hour a few times, but then I will hope to balance this out by having slightly shorter sessions. So hopefully overall it will be more or less 50 minutes per session, but today we had this introduction up to 10. Okay, so now so what we've done here is sort of fix the distribution of the y. So now, we could ask ourselves, given the distribution or a distribution for y, is it sensible to model the expectation of the y given x? Okay, so you will see that even though we're doing practical statistics, you should always be wondering about your model. Yeah. Okay, so is it sensible to model the expectation? I mean, why are we not modeling, say, the median or the mode? So I need to take a little detour here. And this is, okay, so let's go a bit more abstract. So let x, y be distributed according to some joined PDF, say. This doesn't need to be a PDF, but just for the sake of the argument. And then let delta go from your sample space to the calligraphic y space. This is going to be, you should have in mind this regression function. And let's have a loss function. What is a loss function? So this is some L that goes from the calligraphic y times the calligraphic y again. Sorry. Okay, this goes to 0, infinity. So this is going to measure, because we're thinking of this delta to be sort of like the regression function, then we'll want to compare its outcome to the y's. So therefore, because its outcome should be living in the y's space, then we will have essentially, you could think of the difference between these two or the absolute value. So that's an example of a loss function. So we'll see one now in a second. So then the risk of this delta is given by this R. Sorry, I'm not being very careful with my writing. So this R delta that we define to be the integral over the product space of this loss function, and then we have the image through delta of a given covariate, and we have, we want to compare the two things, so the image and the y, and we're going to integrate this with respect to the joint distribution. Yeah, remember this is a PDF actually, so we have the x dy if we like. And then an important fact that we have, this is from so-called decision theory, so those that did part 2 in Cambridge and took principles of statistics, then they would remember this. So decision theory, what it tells us is that, so you don't need to know decision theory, by the way, for this course, but I'm just mentioning this. So if we have that this calligraphic y is in the real line, and let's take the loss function to be, so delta here is not a function, but just a number. Now for a second. So if we take it to be the difference between the 2 and the square, which is what is called the quadratic loss, which gives rise to the quadratic risk, then R, so our risk, is minimized by delta x equal to the expectation of y given x. Okay, so what we've seen is that, in this framework of decision theory, which is the right way of formalizing these decisions, and an estimator is a decision, actually the best decision that we can make in terms of what the value of y should have been is this conditional expectation. But this is, of course, linked to having this quadratic loss, yeah, or quadratic risk, which is a very natural risk, right? Because you could have taken just the absolute value of the differences, but then that absolute value actually is a lot harder to deal with. So mathematically, we generally prefer squares because you can differentiate and get nice results. And in fact, it's very linked to the normal linear model that we had before, right? So the way one finds the optimal line here, well, not the optimal, but some line that seems to be satisfying, is precisely by minimizing the sum of the squares of these errors that we have here. So the dots in red, yeah. And then if we are in the normal linear model, then, well, actually before that, so in the linear model, we have this is called the ordinary least squares model or solution. And if we're in the normal linear model, then that solution actually is the best solution among all of the unbiased solutions. So it has minimum variance, and this is what is called the blue estimator. So you should be familiar with all these things. Again, you can find them on statistical modeling notes. Okay, so but this justifies precisely what we're doing. Yeah, so we, once we fix the distribution, we wish to look at the expectation, because that's really the conditional expectation, because that's really the best estimate that we can have. And then if we're lucky enough, then we'll be able to also have a free parameter for the variance, which is precisely something like the risk here. Not quite, but something like the risk. Yeah. Okay. Okay, so the chat is again not active, so that's good. So let me now introduce then these so-called exponential dispersion families. So exponential dispersion families, family of distributions. So this is EDF. I will shorten it as that. Okay. So I need to give, I like being complete in when I explain things. So I need to give a definition for this that actually is, most of it is non-examinable, because it assumes you have knowledge of measure theory, which is not really needed for this course. Yeah? I mean, it is useful because we'll mention things about measure theory seldomly, but we will. Okay, so as in, don't be too scared if you don't understand what I'm going to write now. All I will tell you what I care about. So let m, lowercase m, be a non-degenerate sigma finite measure on Rd, d greater or equal to 1. So what do I mean by this? Well, sigma finite measure, it has its own definition from measure theory, but if you haven't seen that, then you should just concentrate on the non-degeneracy. And this just means that the m is, some sort of measure, some sort of, just imagine some sort of function. It's not quite that, of course, but some sort of function Rd that is not really just concentrated on a single point. That's what non-degeneracy means. Yeah. So it just sort of spreads out through some region of Rd, or the whole of Rd, if you like, as well. Okay, so what is the assumption? So is this together with, so what we wish, this m is to be such that this set that we're going to define, so it's a set capital theta, and it's the set of thetas in Rd, such that k theta, where k theta is defined as follows. So it's the, sorry, not that. So we have the logarithm. So the logarithm over the sample space of this exponential. So we have this vector product or dot product. And then we integrate this with respect to the measure. So we want this to be finite. So if we look at all of the thetas for which this quantity is finite, then the assumption is that this is open. Yeah, it's an open set. Yeah. Okay, and we're gonna define also. So let this. Okay, this I need a new line. So let this capital phi be the following set. So it will be the set of phi's that are strictly positive, such that the k function, if we rescale it by the phi, then this can be written as the logarithm over the sample space of, this dot is just the same dot as here. So this is the dot product with some z. And so it can be written that rescaled k as this for some m phi that is non-degenerate. Okay, let me just say for some non-degenerate sigma finite. Just the same as above, yeah? But maybe for a different m that may depend on the phi. Yeah. Okay, so let me now finish the lecture just with the definition. So definition 1, for some k as above and known, okay? And that's important, that is known. So we'll see an example in which is, because we don't know it, then it's not really this type of model or this type of distribution. So then this calligraphic P that is defined as the set of distributions indexed by theta in our capital theta parameter space and phi in this capital phi, okay, is an exponential dispersion family of distributions with so-called natural and also dispersion parameters or spaces. Okay, we'll understand this in a sec. Theta phi, theta and phi, or if I'm talking about the spaces, then it's the capital theta and capital phi. If we have that for all theta and phi, the density of, or the density F, which is of course, depending on theta and phi, so it may be different, of P theta phi with respect to some dominating measure so there are dominating measures, and one of them is M phi, so it's not an empty set, the set of dominating measures. So if it satisfies this F, that it can be written as follows. So this is a function of Z and phi, and we have an exponential here of the following quantities. So this is 1 over phi Z transpose. Actually, generally one writes the theta first. So theta transpose Z minus K of theta. And this is now, this is for all Z in RD for some, and this is for some H, yeah, function H. Okay, so I appreciate that this is a bit of an abstract construction, but it is what it is. I don't really care if you don't understand completely what's going on in terms of the measures. That's not what I care about. What I care about is that you understand this F. Just imagine this is a usual probability density function, then it can be written as I've written here. Yeah. So we'll give some properties of this in the next lecture and examples, and then we can introduce the general linear model, generalized linear model. Okay, so thank you for your attention today, and I'll see you again on Monday when we'll have another theory session, by the way. So Wednesday, I said are ready for Wednesday, and this is because the first practical session will be then. Yeah. Okay. Right. Good seeing you all.